So let's talk about your okay, so it starts with getting the right rate of change function graph, negative 32x. Should it look something like this, right? Negative 32x. That was the rate of change function of the following object. Is that correct? So then I left it up to you to decide how you wanted to create the step function. And what's the purpose of the step function again? What does the step function do?
Gives you
Amos. Gives you constant rates, but okay. What's that?
Over very small intervals.
Okay, it could be large intervals or small intervals, but what's the purpose of it?
at a given point in time, it gives you an approximate constant rate for that given time.
Okay, yeah. So he said we're trying to approximate the actual rate of change, right? We're using a step function to try to simulate or pretend like what the actual rate of change is. And the reason we do that is, Stanley. So why do we want to make this approximate pretend rate of change function with constant rates?
That way we can find out how much is accumulating over each interval.
Yeah, so with constant rate of change, we've got the mathematics is easy, right? We all know that delta y equals k delta x. That's what rate of change is. The changes in y are proportional to changes in x. So given the change in x, we know exactly how much y changes with constant rate. So did I specify, what is this, seconds? Did I specify half a second, or did you get to choose that too? So half a second. So I used left, okay? And I found those changes. So in the first half second, I had 0 change in height. Then the second, dropped 8 feet, then 16 feet, then 32 feet, then 64 feet. So if you did it by left, you should have gotten this for your delta y's, right? Your delta y's. And then we said that really our goal and everything we're doing here is, given the rate function, our goal is to come up with an accumulation function. And so we've done that a little bit so far with this approximating rate function. So one way to do that is just get those points. So if it started at 120, after half a second it's still at 120, and then half a second later it's dropped down 8, and then half a second later dropped down 16, then 32, then 64. So that's one representation of the accumulation function. So notice that accumulation doesn't necessarily have to mean increasing, right? We can have decreasing. Accumulation is a general term that can mean increase or decrease. And how, if things are accumulating and decreasing, how is it that they decrease? What's that? Bit by bit still, right? Bit by bit, okay? It's still going to decrease bit by bit. So this is one representation of our accumulation function. We were given rate of change of height, and so our accumulation function will be a height function. And we've also done lots of these, right? So here's another. This is actually now filling in the spaces, so we can represent it with ordered pairs, or we can create our piecewise linear, right? Piecewise linear function. And so this represents in the first half second no change in height, okay? According to my approximating step function, in the first half second it was 0 feet per second, and then in each half second we show a faster and faster downward rate, right? So did anyone do right sides? You did right sides? Okay, in the first half second, what will that look like? So somebody who didn't do right sides. In the first half second, if you chose the right side, what will the approximating accumulation function look like? So I'll do it in red. So what will that look like over here? Sharon, if I use the right side.
The line would start from the right side and extend.
Yeah. So would it be showing too much decrease or not enough decrease compared to the actual? More decrease than actual, right? So from here, what would that first little part of the accumulation function look like? Daniel in the red shirt. So now I'm doing the right side. So there's that part of the approximating rate function. So what will the corresponding accumulation function look like?
It should start off with kind of more of a downward slope initially.
Yep, so it'll still start at 120,
Yeah, it should still start at 120.
but now it'll actually be going down, right?
So it should go down to the second point on the blue graph, correct?
You're saying even with this point?
Yes.
Yeah, good. Yeah, nice. So whatever this came down to, which was
96 or 112?
112, so I went a little bit too far, but yeah, so down to 112 right there. Okay, and then, so this one is going to show too much decrease or not enough compared to actual. Too much, because every one of these constant rates is how compared to the actual rate function. So if you do the right side, every one of your constant rates, greater, well, be more specific, greater how?
More negative.
More negative, right? More negative, right? So more negative means that we're approximating it to be dropping faster than what it actually did, and so then your accumulation function will show more faster decrease. And does anybody remember at what time it hits the ground?
It was like between 2 and 2.5.
Right somewhere in there?
Yeah, 2.5.
That? Alright, so those are supposed to be straight lines. So just pretend those are straight lines. Okay, so tell me about so the idea here is that there is an actual height function, an actual accumulation function. We used the left sides to approximate it with the blue one. I used the right sides to approximate it with the red one. So what about the actual accumulation function in this particular case? Chelsea.
Wouldn't it be the most accurate to use the midpoint?
So she's saying come back here and use the midpoint. Use the midpoint, and that she's saying that would give a more accurate accumulation function n. And then what would that? How can you say what that would look like then in the end?
It'd be the grade between the two.
Yeah. So the blue one is clearly not our approximating of not dropping fast enough, so it's going to stay higher longer. The red one is dropping too fast, so it's going to be falling. It's going to be too low sooner, right? So so we could say the actual accumulation function is going to be somewhere in between. And maybe the midpoint would do a better job. It would find where that is. So somewhere in this range here, there's a true height function. In the black zone, there's a true height function. Okay? And that's our goal. And so we want to understand this process, but we want Graphing Calculator to do the work for us. Because how are we going to get, besides doing midpoint, what would be another way to get more accurate? So, yeah, Christina.
Smaller steps.
Right, smaller steps, okay? So the smaller steps we take, the better those steps are going to reproduce the actual rate function and get us closer to wherever the actual height function is. So let's do, how about steps of 0.1? So how many in 5 seconds? Steps of 0.1 second. How many delta y's will we have to calculate? 50, right? Ready to do that? So we're going to take the rest of class to do that? No, right? So let's now that we understand the process, let's have Graphing Calculator do this for us, okay? So but we have to understand how to write that code. Okay, questions about this homework problem? So approximating accumulation function, we want Graphing Calculator. We're going to tell Graphing Calculator, program Graphing Calculator to get us actual accumulation function. Not today. I mean, we're moving closer and closer to it every day. Okay, this is the journey that we're on. Okay. And then the other part of the homework, as we're doing this, we'll hit that later in the class period. So get out Graphing Calculator, open up your laptop. So here we go. So we're going to actually do something significant here. Now, everything we've done is significant, but we're going to do something very powerful, right? So something so we don't have to do this stuff by hand to get accuracy, okay? So the first thing we want to do is, where do we start with? So in this whole process, where have we started? With what? What kind of function? We started with a piecewise function. Agree? Right? Started with a piecewise function. Everyone agree? No, we didn't start with a piecewise function. We built a piecewise function. What did we start with? Piecewise function is our accumulation function that we built. What did we start with? A rate function, right? We know how fast something is changing, and we want to know how much of it we have. So we'll call our rate function capital R. Oh, by the way, if you go to Graphing Calculator here, if you go to File, Document Settings, there's one feature that I want to point out where you can show the graph below with the equations up above, or you can show the equations to the right, so that the graph is to the right and the equations to the left. So for certain files that you build, it's kind of more convenient to do one or the other. So we'll put all our equations on the left side, and the graph will show up on the right. So we want a rate function. So R and then parentheses, Control 9, Shift 9. Control 9. So this is kind of an interesting function. We'll do e to the cosine x. Okay, then we also want to specify the starting point. What do we call the starting point? What we call the starting point? A. Okay, so whatever. A equals 0.75. Doesn't matter. Okay, we're gonna change that anyway. So start at 1, start at -1, 0, but A is our starting point. Okay, when I hit enter, is this gonna graph? No. No graph, right? So how do we graph it? Yeah, so we want to graph the function by saying y equals the function. Again, Control 9. But we don't want to show it for all x. What x do we want to see it for? Which x values do we want to see it for? What's that? So should I put in greater than or equal to 0.75? So you're missing the power of assigning it to value a, right? So you want to do x is greater than or equal to a, right? So that way, when we change a, then it automatically will do it. Otherwise, we have to change them both every time, right? Now to graph it. Then let's make the graph blue. Okay, so what kind of function is this? What is this showing us? Rate of change, right? Rate of change. So, in this first part here, accumulation. Is it increasing accumulation or decreasing accumulation? Think before you speak. Is it increasing accumulation or decreasing accumulation? Meaning, is it like snow, or is it like the falling object? Jacob. Okay. Right. Right. So why is this is like snow increasing? Why?
Because it's above the x-axis.
Yeah, because the rates are positive. The rate is positive. It's just that positive rate is decreasing. So we said our accumulation is increasing, but it's slowing down as it increases, right? Okay, cool. So here's the great thing. You said to make a more accurate, and so we can change, go ahead, go up here and change it to, say, -1. Change a to -1. And automatically we'll start it, because we set x greater than or equal to a, it'll automatically start our function wherever we select a to be. Okay, so what is the key to making a more accurate accumulation function? What is the key to making a more accurate accumulation function? Smaller delta x. So what we can do is we can set up delta x as a slider so that we can control exactly how big and small delta x is just by sliding the slider. So for those who have a Mac, to get the delta, it's option J. Option J. Has anyone figured out on a PC how to get the delta symbol?
It's not even in like the help thing.
It's not, okay. So if you're doing it, if you're on a PC, you make a character string, do your backslash, and say you could do dx, and that will stand for your delta x, or you could write out delta x. So I'm going to use the actual delta symbol. But if you, like I said, on a PC, you can do dx or delta x. So we want to say equals, and then type out slider. So I introduced you to this on the first hour exam, that you can have as many sliders as you want, not just the end slider that shows up down here. Okay. So then we want to say what the starting value is going to be.
Controller shift.
That's just shift. That's just parentheses. This isn't a function. This is just we're setting the parameters for the slider. So it starts at 0. So a delta x of 1 is for this scale would be pretty large. So we don't need to be any bigger than that. And then we need to tell how many increments between 0 and 1. So we can say 50. Okay, and then when you hit, what happens? I think we need a backslash on this here. So let's try. I'm going to try backslash option J x. There we go. Yeah. So if you do delta x, you still have to do the backslashes on either side so that the whole character string is the one quantity. And then you see that the slider will pop up to the right, and that will control this delta x from 0 to 1. So go ahead and set it at 1, and you should be able to see over to the right there the current value, right? So whatever value you've set it at is here. So if I slide it, it shows me what the current value is. All right, I'm going to make my, let's see. Okay, are we good so far? Everyone with me? So we got our rate function, we graphed our rate function, and now we've set up this very powerful thing of making delta x a slider. So we're going to set up our approximating rate function, and then to do better at approximating the rate function, all we have to do is slide the slider, right? Okay, so
How did you get the little slider piece over it?
if you set it up right, it just appears. If you do this correctly, it just appears.
I forgot the other.
Yeah.
So that, what's in the parentheses is telling graphic calculator between 0 and 1, create 50 little.
Yeah, so 0 is the least value that delta x can take on when the slider's all the way to the left. And 1 is the greatest value. And then how many steps in between. Yeah. Other questions? Okay, so now, yeah.
Does it show up on the graph?
We haven't graphed anything.
Okay.
It's just like assigning a parameter, but it's a changing parameter. It's just like typing in b equals 3. It's not going to graph anything.
So it's just
Right
It's
now, it
just-
doesn't do anything yet.
It's just assigning value, wherever the slider at, that's the current value of that parameter. Okay. So now what you did for what we worked on last week was or you did in your homework, was let's create the points that are going to mark on the x-axis, they're going to mark off the intervals. Remember this? So this is what was a little task you had in your homework. Lots of explanation for a little task, right? So to come up with these points. So how do we graph a point? Control 2. And remember, so I said we don't want to graph them all separately, we want to do it all at once. So let's make a parameter, I'm going to call it C, and then we want is a member of. Okay, now there's different ways to do this. I think the most convenient way is just to let C be integers. Okay? So 0, 1, control, and so let's just go up to just make sure we have enough. 400.
that one's
So that was control, remember, control semicolon gets you the dot, dot, dot.
And what is a member of again?
Control equals.
Control Shift E.
For PC?
Yeah.
Control Shift E is a member of for PC. Alright, but now I haven't specified how we're going to get the right points. Okay? So we want to get these points that mark off our intervals on the x-axis. So let's start with the easy coordinate first, which is what's easy? If all the points are on the x-axis. So what's true then if all the points are on the x-axis?
Y is always 0.
Okay, many people are saying y equals 0, right? So we'll put y equals 0 in. So the question is, what is x that's going to get us the right points in the right place? What are the two things that are determining where these points go? A and delta x, okay? So this is the idea of a function. This is the idea of a function. So the idea of function is everywhere in this. Not only are we trying to create a function, but in order to do that, we're going to use lots of little functions along the way. Okay, so function is not just some excuse to have problems for pre-calculus. It's a very, very powerful mathematical idea that we need when we want to do something repeatedly. We want to repeat a process over and over again. Okay, and so that process is all about what? Input and output. So in this little function that I'm going to come up with to get these points in the right place, what's my input in this particular process to get my points in the right place? What would we think of as the input? Anybody? A? Are we going to put in different values of A, and those are going to get us the different points? What is our input into this process that's going to generate these points on the x-axis? So we need a first point, right? So we're going to have a first point, and then a second point, third. All right, so how about what's the output? Let's start with the output. What's the output of this process? The x values, right? The x value of the point. So what is our input that's we're going to have a rule that's going to create these x values of these points?
A plus delta x.
No, that's the rule. You're trying to come up with a rule. All I'm asking for is, what will our input into that rule be? C, right? We're going to have the 0th point, the first point, the second point, the third point. See, these are the inputs of this repeated process. Each one of these is going to give us a point on the x-axis. Where do we want that first point? What x value do we want that first point to be at? A. Where do we want that? The 0th point. So then the next point over, which is where C is 1. A plus delta x, right? Then the third point over, or 2 over from the left.
A plus C delta X.
A plus 2 delta x, right? Yeah, because so at the 0th point, we just want it to be A. At the first point, we want it to be A plus delta x. So at the C point, we want it to be, Adonijah?
A plus C delta X.
A plus C delta x, right? So this kind of reasoning, when you're creating new stuff, when you're a manager of calculus, this is the kind of stuff you do all the time. So I'm just, the best I can do is I can point it out to you and we can do the process, but somehow you've got to have this mentality when you're solving problems that, oh, this is a function and I can set up input and output and come up with the rule to do this process many times. So my x coordinate of every point is A plus C delta x. And let's make the points red. Okay, was anyone's solution to that like this? Did anyone come up with a solution like this? It's okay, so but this is the most efficient because we can just basically, we're numbering the points and then that gets us each one of them based on the changing value of C. Yeah, Daniel.
Is it okay for in the x value you just say C and then where it says 0, 1 you just say A and then A plus C change x dot 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 forward?
You were putting some kind of rule into here.
Yeah.
Yeah, it's okay. It'll do it. But I'm saying this is a more efficient way to do it. Think of your inputs as just being the integers, and then that will crank out each one based on whatever the value of C is. Does it work? Right now, what is delta x set at? At 1. So now we've got something graphing delta x, so delta x should show up when we change it. So now I'm just going to make delta x, say, now it's 0.58. How about, there's 0.16. So here's 0.5. And it puts it just where we want it. It starts at A, and so then we change the value of A. Make A 2.2. And now it starts at 2.2. Change the value of delta x. So, aren't you glad you live in a day and age where you don't have to do all this stuff by hand, right? So, 50, 75 years ago, users of calculus, they were the computer, and they had to do all these kinds of things by hand. Okay? So, we had the luxury of understanding it and then letting the computer do the work for us. So here I'm starting at 0.25, and I've got a delta x of 0.5, so we can change it however we want. Okay. Any questions so far? So you got to be really confident you understand and can recreate what we've got so far. Everything should make sense. So now we want to talk about, so what was the next thing we want to do if we want to create the accumulation function? What's our next step in the process? How about Andrew? Over here, this Andrew. So we got our actual rate function. We've set up some intervals. What would be next in moving towards an accumulation function? He said to estimate constant rates within those intervals. What do you think? Yeah, that's the next thing. We want to come up with our approximating rate of change function that approximates with constant rates. So here's something that will help us understand how to do that. So here's if a was equal to 0, and then delta x was, say, 0.5, okay? So delta x is 0.5. What we're trying to create next is our step function, okay? Step of x. And so what's that? That's the constant rate function. In this case, we're going to have it be according to the left sides. So what I want you to do is use the rate notation, the Rx notation, to write out what would the value of the step function be, okay, for each of these x values using the Rx notation. See if you can do that. See if you can write out what the y values of the step function would be at each of these x values, given Rx and delta x at 0.5 and left sides. See if you can do it. If you understand what's going on, you should be able to do this. So it has nothing to do with the e to the cosine x that we graphed. This is just a general exercise. Using a generic rate function, what would the values of the step function be for these x values? Okay, think about it. So it may not come instantly, but think about it. See if you can do it. Who thinks they have an idea? One person? Anybody else? Chelsea, 2, 3. Talia, what was your idea?
Just that you would do, so your A is 0, so you would do 0 plus, for the first step it would be 0 minus 0, over delta x is 0.5, and then 4 of that.
But now we're actually talking about what is the rate. So you're talking about the x values like for the left side, which we already got, right? We already got those points. Now we're actually asking about what will the rate be at these different x values. Does that make sense? So what you're talking about is finding the x values of these points, which we already have. So the next step is we want to get the rates, right? We want to get what those rates are in the step function. So that's what this kind of little exercise is about. Dan, you about to raise your hand? Oh no. Anybody? Daniel?
Perhaps the values for 0 through 0.4 are all R of 0.
Okay, so stop right there. So he said the values from 0 through 24 are all R of 0. Adelaide's giving me eyes. You don't understand. So Daniel, why?
Okay, so you're creating these boxes that are 0.5 wide.
Okay.
And
Intervals are 0.5 wide.
the interval has a constant value.
Constant value.
The left side. So if the left side of the interval is 0, or R of 0, just every value that falls under that box is R of 0.
He wants every value through here to be R of 0. What do you think? Agree?
Yeah.
Yeah.
They're starting to comprehend.
So at point 3, it's going to be the rate. How are we going to get this rate at point 3? How are we going to get the rate on the step function at point 3 if we have delta x at 0.5 and we're using the left sides?
It's just going to be the same rate as 0.
The same rate as 0, he's saying. Dan, you like it? Or Tyler, you like it? Okay, can you finish it now? Can you finish it now? Does it make sense? This needs to make sense. Where did I lose you?
I don't know, I'm just lost,
It's because we don't have a graph in front of us now.
maybe.
Okay, so let's put a graph on here. I'll just draw a graph real fast. So here's 0.5, and here's 1. Okay? So suppose we have like this. Now, if I'm using left sides and an interval of 0.1, what will the rate, the approximating rate, look like? If I'm delta x is 0.5 and a equals 0, and I'm using left sides, can you imagine what the approximating rate function will look like? Megan, could you tell me? Okay. Like here? Here? And what would you do? How? Up like this? Horizontally. And then what would it be? Something like that, right? So I'm asking, what is the value of the step function at 0.3? Do you see? Is this better now?
Yeah.
So what is the value of the step function at 0.3? See that it's r of 0, right? It's r of 0. So can you finish it? So finish this row in the table. Go.
We're looking at the value of at 0.5.
Okay, Savannah, what will step be at 0? R of 0. Because that's like this point right here. It's the same, right?
Yep.
Okay? Helios, step of 0.1. R0. Olivia, step of 0.2. Who's that? Kaiser, step of 0.4.
R of 0.
Cool. Katie, step of 0.5. R of 0? Agree? That's where we jump up to the next one, right? So from 0.5 on, so it would be R of 0.5. And Marcus, until what?
0.9.
And so what about R of 1?
It'd be R of 1.
He wants R of 1. What about R of 1.3? Okay, all of those. Does this make sense? So here's what we need then. So we need to, how is it that we're going to use x then to get what we need? So we need the input of the function to be x, and we need the output to be step x. So what we need is we're going to need an intermediary. Remember, that's our left function. So what's the input into the left function? What's the input? Christina, what's the input into the left function?
Wouldn't it be like anything less than 0.5 to 0?
You know, what quantity goes into the left function? So what goes in? No, just in general. Stanley.
X.
Yeah, so what goes in is x, and then what's going to come out? So is it a rate that comes out? Does a rate of change come out of the left function? What comes out of the left function? Step, a rate? Comes a rate? Left is a rate function? What is it? So what kind of thing is that comes out? What's that? Another x, right? So the left function, the input, don't miss this, because this is going to help you understand it. What goes into the left function is any x value, and what comes out is another x value. Which x value comes out? The rate of change. Is that what comes out? The rate of change comes out of the left function. No, not the rate of change. X goes in, and another x comes out. Which x comes out? Whatever's on the left end of the current interval, right? So we're going to put 0.9 in to left x. What's going to come out? 0.5 is going to come out. So it's basically what's going to come out of this function, this left function, is going to be now the input into our rate function. That's why we need this. Because we need to get from the current x value to what we're going to put into the rate function to get it right. Do you see? Okay, can you create that row? So can you write out what that row is?
But technically the 0.5 is the constant rate for that interval, right?
No, it's an x value. R of 0.5 is the rate.
We don't have the rate function in this case.
0.5 is just where we're at the x-axis. And then the actual rate function has some rate there.
Oh, okay.
So 0.5 is just where we're at the x-axis. Okay, so can you finish that row? Can you do that row? Okay, so if I've lost you, ask a question. Okay, so find someone to talk to and figure this out. So put your heads together. Get a partner. Okay. How about this, Andrew, back here? Can you tell me you're thinking about this middle row here? Okay, he's saying it's just going to be the x values of what we're putting into the one below. Some people are agreeing. Will they all be the same?
No.
Where will it change?
At 0.5. Every point.
Okay, so this is a kind of a two-step process. We have the current value of x, and first we need what? The value of x at the left side for that current value, and that's what this is. So we put x into the left x function, and what comes out of that function? What do we get? Another x, but now it's at the left side of the current interval. And now we're going to take that and put it into the step function so that we get a constant rate of change, right? We're going to always get that same rate, the rate at the left side. So what comes out of step x? Right. And that creates our step function. So starting with any current value of x along the x-axis. First getting the left side for each current value, and then putting that into our step function. Pulls off the rate at the left side, and creates this, what I'm showing in red there. Okay. Does it make sense? Is that a question?
Yeah.
Okay. So, what do we need? We need the left x function. So left, oops, backslash left, backslash. We'll call it the left function, L-E-F-T. Control parentheses, x. We took a couple classes to develop this, so we'll just write it down. Remember, it's a plus. To get the floor function, you just type in the word floor, and it appears. Okay? And it was x minus a over what? Shoot. I can't seem to get... There we go. Divided by delta x. Then what? Okay, and we worked hard at understanding where that came from. There's our left function. So, just if you type in the word floor, then those braces come up for the floor. So, backslash. So here's our first crack at accumulation function, or sorry, step. We'll call it step. Based on what we just learned, can you write the rule for the step function? Can anyone do it? So, based on what we just did with all that stuff on the spreadsheet, can you write the rule for the step function? Can anyone do it? Extra credit if you can do it. You paid attention. So, let me see. No, just speak to yourself. Speak to yourself. See if you can do it. Yeah, I want to see if anyone can do it. If you understood what we just talked about. We got one. One person's got it. Two people. Three. So, what's the input into this function? X, right? And x goes into what first? Left. And then what do we do with left? Plug it into R. How do we write that?
Step of x. Oh, you already have that part. R of left.
R of left.
Left.
Don't forget control 9 on both of them. And we'll make this purple. Is it going to graph it? How do we graph it?
Like step.
And we'll do that purple. Okay, so there's a couple issues that we don't have time to deal with today. So something about this, a couple things about this should make you go, that's uncomfortable. This doesn't look like what it's supposed to look like. So one of them's easy. What's the first thing?
It continues on past the end.
Yeah. So what do we want to change here?
We want to cut it off. I can't see where you are. 0.5 or 0.25.
So I'm going to put greater than 0.25.
Or you can just do A, since you already defined it earlier.
It's not that you just can do it. That's what you want to do, right? That's what you want to do. So that's the first problem solved. But now we got a kind of bigger problem to think about. And we'll pick that up on Wednesday. So make sure you fully understand everything about this and could recreate it, okay?
My bicycle.
If you're dying to have your quiz now graded, you can come up. Otherwise, I'll have them again Wednesday for you. Beth. How's your...
Should we save this?
What's the last name, Chelsea?
Rogers.
Sure. Alphabetized wrong. Some others. Oh, and why? Yeah. B? B. Last name? O. What's that? Last name?
We had the movement.
F?
All the same. We had that one.
P.
I was just so excited. Oh yeah, by the way, I'm going to be here last weekend. Yeah. But I'm like really like nervous because
Family. Last name?
Did you? He told you? Oh, yeah.
I'll be fine. I know.
I had like a 1:30 though.
I'm leaving like on Wednesday night.
That's. What's your last name?
And then I'm
L.
going to come home and finish packing everything and then leave pretty early the
Good.
next morning. On,
Anyone else want their quiz?
but I don't know. I mean, I think I'll be well rested. If I can sleep.
So she needs to come give you a
It's too
wake.
excited.
Tyler. Your quiz. What's your last name, dear? Nice. Excellent.
I need to go like
Last name?
the whole front.
Yeah, so don't forget. Everything builds. We gotta keep. Don't forget what you've done before. Anyone else want their quiz?